Thank you, Amelia. Um, Hello, everyone. Let me first welcome all of you who attended the webinar. As a member of our digital services group, I'm glad to be back here again with another webinar. I hope you enjoy it. Today, I'll be presenting some fundamental concepts in anomaly detection at large scale in a multi-sensory environment. The purpose of this webinar is mainly feature learning from the massive amount of sensor data and to be able to help industry to develop condition-based monitoring and improve business strategies. I'll begin with a brief introduction about ourselves, who we are, what we do here in Scotland, and then at the end of my talk, there will be a Q&A session, as mentioned by Emilia, and you could drop me your question. Please get in touch with us after this webinar if there is any inquiry, and we will get back to you with an answer as soon as we can. So first of all, we are a UK National Engineering Laboratory since 1947. We are also known as NEL, which is a subsidiary of Tufsuit company from 1995. We are also UK's National Measurement Institute for Flow and Density Measurements. National Engineering Laboratory is involved in different areas. Our focus tends to be flow measurements previously, but data science, sensors, and the instrumentation that we have are utilized through any types of industry and different sectors. Therefore, our methods can be applied to all different sectors and industry. We work in oil and gas, but we actually shifted our focus onto clean fuels and life science as well as digitization in the past few years. To the next slide. Here is a picture of our one of our laboratories. We actually have our own facilities here in East Kilbride, Scotland. Our own engineers design and maintain these facilities, which allow us to better understand our data from temperature, pressure, and other types of sensors, mechanical equipment, and so on. And as you know, both sensors and mechanical equipments are standard components in all industry. Which again, it means that the data that comes off the equipment and analysis technique that we use here are applicable to any sector. So below are senior members in our team, our digital services team, including myself, which come from different backgrounds with diverse skill sets. We believe that these diverse skill set by our team members is a bonus for everyone who wants to work with us. We are not just modeling the data blindly, we actually relate it to underlying physical process, and our engineers from different groups help us better unveil the more useful aspects of our data. We also, as I mentioned, come from a different background. I myself specialize in uncertainty quantification, data-driven modeling, Bayesian statistics, and condition-based monitoring. And our group is led by Gordon Lindsay, head of digital services group. He's specialized in electric and electrical engineering. And our mathematician, Yan-Feng Lang, is specialized in data-driven modeling, predictive maintenance, and machine learning. So I give you a brief introduction about the purpose of this webinar and the areas that we focus, the types of feature learning we cover here. I begin with introduction into characteristics of multisensory systems and the important component in multisensory systems, types of anomalies, and anomaly detection systems available in the literature, and the types of anomaly in sensor system, to be more specific. We also look at some conventional and also some advanced data-driven modeling techniques to deal with anomaly detections. And we also explain some abstraction algorithms such as recurrence plot, spectrograms, and signature matrices to extract useful information from multisensory data. So first of all, let's talk about the sensor system in general. So electronic systems and sensor systems have become major generators of data with yearly rates on the zettabytes scale. Because of the hyperconnectivity of the Internet of Things, you know that there are massive amounts of data being stored every day. In the context of IoT applications, sensors are the real source of big data, and neighboring devices can communicate with each other and transfer data to a cloud infrastructure for further elaboration. So this amount of data has made the big data sensor system play an important role in modern interconnected digital infrastructure. For instance, in environmental monitoring, smart cities, factory automation, autonomous transportation, and intelligent buildings, we have loads of sensors and loads of data that are stored in the real time in a database or in a cloud infrastructure. Other examples include wireless sensor networks, multi-sensor glucose monitoring system in health sector, and in our manufacturing industry, we are all familiar with the term called CBM, or condition-based monitoring, that requires modeling big sensor data. So we have all these great examples of multi-sensor systems and their application domain. So characteristics of multisensory system. Uh, we are all aware of time series data, multivariate time series data, and we already discussed about the main characteristics of multivariate time series data in our previous webinar. We talked about the importance of temporal information and automated way of learning temporal information from the data. So temporal information is one of the main characteristics of multi-sensor data, which actually are multivariate time series data. Another important aspect and characteristics of multi-sensor system is spatial information, the information that depends on the neighboring sensors. So these neighboring sensors may have a spatial correlation with each other. So if you look at the right, the figure on the right hand side, you will see that it's a 3D layout of one of our laboratories. So you will see that sensors A, B, and C, which are in the far end of the facility, share common statistics, and they have same very common statistics like the periodic characteristics and the frequencies. But as we go farther from the facility, to the right hand side, we will see that signals Y and Z uh, have different characteristics compared to the A, B, and C. So this is a spatial correlation that exists in a multisensory system. Those adjacent sensor at the far end have higher, probably they are more likely to have more similar characteristics compared to the sensors in the other end of the facility. So this is applicable to any types of sensory system like wireless sensor networks. So on the left hand side, we have a correlation heat map for these spatial correlation, and these are actually from our own real data sets. So we can see that the main diagonal of this correlation heat map, sensors which are placed nearby each other have higher correlation, and we can see as we go further from the sensor, neighboring sensor, these correlations become less and less severe. So sometimes the system faces abnormalities that are often rare or difficult to model, or sometimes it's difficult to predict the situation in the system. And also these failures that come across may have, and their root causes may lead to very costly consequences if they are not detected. So that's the importance of anomaly detection in these types of systems. Anomaly detection is concerned with identifying data patterns that deviate remarkably from the expected behavior. So everything we talk about here for anomaly is how the system behavior deviate from the expected behavior, and it shows an irregular pattern. Anomaly detection is an important research problem due to its broad set of application domains, from data analysis to e-health, cybersecurity, predictive maintenance, fault prevention, and industrial automation. We have different types of anomalies. Here, I like to talk very general. You may find very different types of anomalies in the literature. I just here point out the most important ones. A point anomaly is where a single data point shows irregular pattern when compared with the neighboring data points. In other words, we see an unexpected or out of distribution data points in the middle of other data points. A collective anomaly is when you look at a group of some data points, you see these irregularity and unexpected patterns, and this becomes clear in the second graph. If you look at the right hand side, we have a collection of points which have a completely unusual trend right in the middle of a periodic signal. So this is an indication of a collective anomaly. And the third type of anomaly, we have contextual anomaly, which occurs when one or more data points are anomalous regarding the context of the system or context of the problem. And the value in the contextual anomaly departs from the rest of data points in the same context. So we all talk, everything is about the context in the contextual anomaly. So if you look at this example for the contextual anomalies, we will see that the data is actually temperature data. So we expect to see this seasonal behavior in the data. So in the summer, we expect the temperature to be higher, and then in the winter, it goes down. But somewhere in the middle, we see the deviation, a very sharp shift in the temperature values in the summer, and that's against the context of the summer, which we expect all the recorded temperature to be much higher than those recorded in the data. So this is against the context of summer, and although the data may look reliable or good in terms of point anomaly or collective anomaly, the shape of data or the behavior of data is contextually anomalous. So when we talk about anomalies in sensors, we refer to unusual local changes in the spatial, spectral, or temporal values. And this is to say that surrounding neighbors of the data have some unusual changes. So this is the case for the multisensory system. And we have different types of anomalies for multisensory system. We may have different definition. For instance, for environment, we have environment anomaly when the state of environment changes or a new component is introduced, or even when a highly unusual event occurs, such as a natural disaster. In a system fault or hardware fault, we have anomalies that are generated by the fact that a component of the system malfunctions or breaks down. The part of system affected can be anything from a sensor to a cluster of nodes, and these anomalies can be generated by hardware faults or limitations in the infrastructure. The other types of anomaly can be communication loss, which are caused by loss or delays in the communication packages. These types of anomalies occur in the system that make use of different communication technologies. And also we have very important parts of the technology, which is cyber attacks or fraud or intrusion. These kind of anomalies are introduced in the system by a criminal party as an external factor. They are created by different means ranging from physical intervention on the system to loading communication traffic. So in the past, we worked with a case study which some fraudulent there were some fraudulent activities such as placing a magnet in a sensor to show unrealistic flow measurements for the oil bunkering industry. So this slide presents different approaches to deal with anomalies, whether conventional or more advanced data-driven approaches. The conventional methods include very well-known statistical techniques or statistical modeling techniques called PCA, principal component analysis. We have linear and nonlinear or kernel-based PCA, which are used for anomaly detection. Statistical analysis, such as interquantile rule, which looks at the out of distribution data points and look at the interquantile range to detect the out of distribution data. We have also a spectral analysis and to extract features in the frequency domain. And for the data-driven approaches, we have more complex, which are applicable to more complex problem. They can be embedded into deep neural networks models such as autoencoders, generative models such as GANs, and variational autoencoders to detect anomalies. So conventional statistical modeling assumes that the data points in a system are generated according to a statistical model. So we talked about PCA and its importance and popularity in anomaly detection. PCA is all about compressing data while preserving it and preserving as much information in the data variation as possible. So it's commonly used for dimensionality reduction, and it actually projects each data point onto only some few principal components. So it's a dimensionality reduction technique to transform a high dimensional data to a lower dimensional data. The assumption here in the PCA is that data comes from a constant multivariate normal distribution. And the other assumption is that principal components are orthogonal. So this probably one of the limitations about the PCA that makes a strong assumption about the distribution of the data and the models. So overall, PCA assumes that principal components with high variance must be paid attention, and the principal components with lower variance are disregarded as noise. These kind of methods, such as PCA, SVM, and KNN, generally involve measuring the reconstruction error between a data point and the reconstructed data point. So we reconstruct the data point from an input data and then measure the error between reconstructed signal and the measured signal to see the error and the quality of signal. This reconstruction, of course, in these techniques are generated from a linear transformation that is fitted on the training data, and then it tries to understand what an abnormal situation look like. The problem here is that the conventional approaches may fail to represent system signature at different temporal resolution. We find out about it more as we go ahead to see what we mean by feature learning from different temporal resolutions. And as for signal processing, we have different types of techniques, such as very popular Fourier transform techniques that are used to transform signals from a time domain to frequency domain, and then extract the frequency content of the signal. And the other method includes digital filtering, which consists of some linear transformation of number of surrounding samples around the current samples of the signal. So the filter suppresses unwanted components or features from a signal to give us a better representation of the signal. There are other techniques, such as the spectral subtraction method, which is a simple, effective method of noise reduction, and also Mel frequency spectrum, which is a representation of the short-term power spectrum. So there are all different conventional approach to extract features from the signal. So now we get to the more interesting part of this webinar, which are automated feature learning from multivariate sensor data. In our previous webinar, if you remember, we talked about some automated feature learning methods. So for multivariate time series data, we talked about temporal information and spatial information. But here we like to explain more in details of temporal and spatial feature extraction and pattern encoding. We like to talk about methods that extract both temporal and spatial information from the data and from different segments of the data. So, and to do that, we use deep neural network models such as one-dimensional CNN, RNNs, long short-term memory neural networks, which are types of RNNs, and temporal convolutional neural networks. So all of these methods that I mentioned, they only account for temporal information. So if you look at the figure on the right-hand side, on the top, you see a model that uses a kernel, and the kernel or feature extractor moves along the time domain. So there is a kernel that slides across the time domain to extract the features. So the thing here is that we only extract, because we just move in one direction here, we only extract temporal information from the data. But when we look at the figure on the bottom, we see the kernel or feature extractor, which slides across both temporal and spatial dimensions. So that's why we say these kind of methods can extract both temporal and spatial information from the data. But we need to think about transforming our data into a useful shape for different types of deep neural network models to be able to extract spatial and temporal information. There are varieties of these models, such as 2D convolutional neural network, 3D convolutional neural network, residual networks, convolutional LSTM, and more recently, transformers, which are methods which are neural network models with differentially weighting the significance of each part of the input data. So before going into some examples about the feature extraction, I like to talk about the concept of system signature, what it means to have system signature in in the context of a multi-sensor system. So signatures help us to characterize multiple levels of system status in different time steps. We have we can extract different information from the data based on the window, the window of the time, or the time steps, the amount of time we look at the data. And in the context of anomaly detection, this is to say that we extract with the signatures, we extract different levels of the system status to indicate the severity of different abnormal or normal incidents. When we feed neural networks with noisy raw data, there is a problem that there might be a generalization capability issue when we deal with temporal predictive models such as LSTM, and their performance may decrease when they are fed with noisy raw data. So compared to raw sensor data, signatures can be better. Can be a better representative of intersensor correlations. They can abstract and represent intersensor correlations in the data, temporal correlations at different temporal resolutions. So if you look at the graph here, we have different. We have a signature matrix here on the left hand side. We see the time window, and the signature is different as we go ahead. We can see a different signature of the system, and this helps us understand the spatial information in every time window. And by changing this time window, we can extract different levels of spatial information. So this is a very useful feature extraction technique to keep in mind. One example of abstraction algorithms such as signatures are recurrence plots, which are which uses algorithm to split data into small scale structures to actually represent the dynamical system. And recurrence plots are graphical devices specially suited to detect hidden dynamical patterns and also nonlinearities in data. They were initially used to graphically display and represent non-stationarity in time series data, but they are also widely used to get an abstraction of the data, raw signal data. The recurrence plots are also known as a very useful method for analyzing linear dynamic system with nonlinear features. They can be used to analyze physiological rhythmic system. We have different examples in mechanical, electrical, chemical, and special activities. Recently, we have seen a recurrent plot method that was used to develop a computer-aided diagnosis system, which then make use of convolutional neural networks, and it has shown to be effective for two-dimensional image processing. So we have a great example of success of recurrence plots in the past. These plots also allows multidimensional machine learning structures such as convolutional neural network to be applied to one-dimensional data, because they transform a 1D data such as time series to a 2D representation. So here we have two signals as an example. So we have the signal one, which is shown in green, and the second signal shown in yellow. We see the difference between these two signals, and the yellow signals gives us which has a linear trend. You can see right in the middle, we see a linear trend in the second signal, and this is very clear when we look at the recurrence plots. So our neural network models can be fed with these transformed representation of data, which we call them recurrence plot, instead of being fed by the raw signal data. This can give us a better, give our models a better understanding of the system status. So we can have a look at some other examples here. For recurrence plots, here I just put some examples of how different types of signal and different recurrence plots for different types of signals. So we have this rectangular pulse, which gives us a recurrence plot, as you can see. And also we have another example, which is a periodic signal. So we can see the texture in the recurrence plots are quite different and completely distinguishable. Another useful tool for as an abstraction algorithms are spectrograms. Spectrograms display changes in the frequencies in a signal over time. So we can have both information from both frequency domain and temporal domain in the same plot. And that's why spectrograms are very useful, especially for audio recognition. So we can also have a clear picture of different segments of the data by use of the spectrograms. But how spectrograms is generated? A spectrogram is generated through short-term Fourier transform procedures, and this data representation can capture, evolving harmonic content over time, and also over the different frequency spectrum. The most effective deep learning method for such inputs, as we mentioned before, are shown to be convolutional neural networks. Because the reason why we transform 1D array to 2D array is that we can use the power of convolutional neural network models, especially two-dimensional and 3D dimensional neural networks that can deal with these types of data. In the seismic world, we have some examples of spectrograms application along with convolutional neural network, and they are increasingly being used to look at frequency content of continuous signals to help distinguish and characterize different types of earthquakes or other vibration in the air. So there are great examples of application of spectrograms for such domains. Recently, a variety of studies have also considered using a spectrogram representation of an acoustic signal as a neural network input. So instead of using raw input time series data, they used spectrograms to feed their neural network models. Another example is robotic manufacturing. For automated robotic manufacturing, a key aspect of monitoring is the identification and segmentation of the process. And these spectrograms can help us understand the different information in different segments of the data. And there are plenty of examples of successful application of spectrogram-based convolutional neural network in the past. And here again, I chose the same signals to show you how their spectrograms can differ, just to give you an idea of how spectrograms look like. As we mentioned, they are come from a short-term Fourier transform. So depending on which configuration you choose for your short-term Fourier transform, you may get a very different shape of and very different image for your spectrograms. So I would suggest doing some exploratory data analysis before building any model to check which data representation are more useful for your specific problem. So as we said, there may be different configuration for your short-term Fourier transform, and requires you to try and error, see which one suits you best. So we talked about signatures and their capability to capture dependency. One great example here is a signature matrix, which calculates inner product of different pairs of time series. So with the help of signature matrices, we can extract spatiotemporal dynamics from the system, from the multivariate time series data. They can also represent intercorrelation between different pairs of time series. So we can see these intercorrelations at different time frames and different segments of time frames. So we see how what it means when we talk about different segments as we go ahead. If you look at the figure, we can see that at time 0, we have a signature matrix of the system which represent spatial information at specific time step. And when we look at the time 10, of course it's a window, so the graph is extracted from a window of time step, not just one specific time step. So when we look at the same spatial information but in different time, at time 10, we see there is a correlation, but there is also a change and shift in the values of the data. So this is how signature matrices can abstract and show us what's happening in the system, whether in spatial domain or the temporal domain. Here we've got an example of application of signature matrices just to sum up our feature learning process for today. We have here we show how these kind of signature matrices can be fed to a neural network model. Here we've got an example of a 3D convolutional neural network. So these signature matrices are taken from different segments of the data. So imagine you have a time window of size 16, a time window of size 32, and the other one a longer term dependency. For longer term dependency, you can get 128, for instance, as time window, and then extract signature matrices. So these 3 different segments are your channels in the 3D convolutional neural network. And also we have the factor of time. So where is the factor of time here? How can we see the temporal information? So when we look at data, we can split the data, which is a time window, to different time frames. So by splitting data to different time frames, we can have another dimension to the data. As you can see in this plot, we have 64 frames, which are representative of our temporal information. And all the spatial information are encoded as signature matrices. So this is how we can feed a 3D convolutional neural network with the use of signature matrices. And of course, because we look at different segments, it extracts multiple level of information from us. So this is a clear example, and we use this in the past North Sea flow measurements workshop in 2021. So you could also have a look at our paper to see how it works and see more details about signature matrices and their application with 3D convolutional neural networks. Yeah. So here in this webinar today, we talked about important characteristics of multi-sensor system and multivariate time series data. This webinar was a continuation of our previous webinar on time series data. So here we covered more aspects of spatial and temporal information. Different types of anomalies in different application domains were discussed to give you an idea of how we can extract different methods to deal with anomalies in the systems. We talked about complex relationships in multivariate time series data and multi-sensor data, and the necessity to extract these information in a fully automated manner with the use of transformation techniques, abstraction algorithms, and so on. We talked about different methods to deal with the spatial and temporal patterns, and we've given some. We compared conventional and advanced feature extraction with their limitation and their advantage, and also at the end we showed some examples of signatures in the system to extract multi-level information from both temporal and spatial domains. So this is pretty much everything I wanted to cover for today. So I would like to hand it over back to Emilia for Q&A session.
Okay, thank you. Yes, so I think it's a great time to start the Q&A. We'll run through any questions. Okay. So we've got one which says, could you explain how signature matrix can perform multi-level feature learning?
Yeah, so if we go to, let me just scroll back to some previous. Yeah, so here, if we look at this plot, this is a very informative plot that shows us what's happening in the multi-sensor data. So we can look at one specific fixed length time window, as we spoke, like 32 of size 32. We can extract some spatial information from this specific time window, but this may not give us a longer term dependency. So we may want to look at a longer term dependency. So we increase the size of time window, or even if we like to have a view of a lower, shorter term dependency, we can decrease the size of time window to 16 or 8, anything that suits us best, and look at the spatial information in that segment. So it gives us information from longer term dependency and also shorter term dependency. So it helps us understand, in other words, it helps us understand multiple level of information from the data.
Okay. Amazing. We've got another one which says, how do you select models, architecture, and hyperparameters?
Yeah, so I myself, if you like to know about more technical details of the work, I myself use TensorFlow. So in TensorFlow, you have a like a package called Keras Tuner that helps you optimize your model with different configurations. So you can have a grid search for your hyperparameters, learning rate, even the architecture of your network. So you can have conditional variables, conditional parameters to let your model expand. Or so Keras Tuner is a very recommended package that can be used to optimize and select hyperparameters of the model. So I really recommend you use Keras Tuner. If you're familiar with TensorFlow, it's really useful.
Okay, and then the last one that we've got for today, unless any come in afterwards, are, can these techniques be used in supervised learning problems such as classification?
Yeah, of course. You know, it's all about extracting features from the data. So as long as we find a reliable way of extracting feature from the data, the application domain can be completely supervised, unsupervised, or semi-supervised. So you just need to change the last layer of your model to make it applicable to your own specific problem. But the main the focus and the main element here is how to extract feature reliably from our massive amount of data that are being recorded every day. uh, you could use all these abstraction methods to extract features, and in the end, if there are some labeled data, you could condition them to the labeled data and build a classification model.
Okay. Well, thank
Okay.
you again, and thanks again for everyone for joining us today. As I mentioned earlier, you will receive a link to the recording of today's presentation, and please don't hesitate to get in touch to let us know if there are any other webinar subjects that you would like us to cover in the future, because it is great to hear exactly what you're interested in hearing about. You can get in touch with me and send any inquiries to info.uk@tufsud.com, and please feel free to visit our website www.tufsud.com/UK for any more information that you could possibly need. And so on behalf of myself and our presenters, thank you very much for your time and enjoy the rest of your day.